I already know with one single element left, I need one comparison. Okay? So this is going to be a very important argument later on. I need two iterations, and since my algorithm is proportional to the number of comparisons or number of iterations, it is exactly just 2 units of time, 2 microseconds, milliseconds, whatever you want to use. Peter's algorithm, on the other hand, will need 3 to confirm the element is not in the array because he's using linear search, and also we may be looking for a value that is larger than all the elements in the array. The amount of time it takes is just linear compared to the number of iterations required. Are we doing okay so far? Yeah. And Bob said, well, Tech, doesn't look like you have any chance of staying with the company. And I said, well, hold on a second, boss. Let's make it 7. Well, why do we pick 7? Because with 7, 1, 2, 3, 4, 5, 6, 7, we pick this one to compare to, which means I can either eliminate these 4 in one single comparison, or I can eliminate these 4 in one single comparison. What is left is 3. Do we know how many comparisons I need with 3 elements? Yeah, we know. So with 7 elements, I only need 3 comparisons. Okay, so 3 goes here. And Peter's algorithm will need exactly the number of iterations is the same as the number of elements in the array. So with this, I can just do the quick calculations like this. He's still gaining a lot. I mean, he still has a big gain, but in terms of the ratio, he's not gaining as much anymore. I'm very slowly catching up. Slowly, very slowly. Emphasis on slow. Okay. With 15 elements, okay, I need 4 comparisons. Okay. Doesn't look like I have any chance of staying with this company the way it goes right now. Okay. So we'll just skip a few items here. We'll skip all the way to 255. With 255, I need 8 comparisons. Now, how do I know that I need 8 comparisons? If you look at the pattern here, 15 is 2 to the power of 4 minus 1. 7 is 2 to the power of 3 minus 1. 3 is 2 to the power of 2 minus 1. 255 is 2 to the power of 8 minus 1. So that's why I know that I need 8 units of time. Peter's algorithm will need exactly 255 iterations. Well, he's still gaining. I mean, we are talking about 8 units versus 0.0038 units. But I'm gaining, yes?
Why don't you just use a faster computer?
Because I don't like to waste anything. I don't want my computer to become e-waste when it's perfectly functional. Besides, real programmers only need VI to write any programs.
Okay.
Yes. What? The 3D6SX? No. For energy efficiency, that's a good reason to get rid of it. Yep.
Would you donate it to like the Smithsonian or something?
I don't think they care much about 386SX. Intel will probably buy back all the 386SX computers and burn them, so that no one has any evidence that they have ever produced a 386 computer. So we'll move on to 36636, or 35, which is 2 to the power of 16 minus 1. Okay, so naturally I will need 16 comparisons, taking 16 units of time. Peter's algorithm will need that much time. And Peter is still kind of chuckling and go like, Tech, you're going, right? Well, let's take a look. How many more times do I have to, double this before I can actually get to stay in the company? I just need to double it 4 more times, right? So we'll go ahead in this case, instead of doing the calculations, I'll just use, the cheap way of doing it. So let's say 2 to the power of 12 minus 1. Oh, that's not going to work. That was dumb. Okay, let's try 20, right? 2 to the power of 20 is 16 times 65,335. And I need a minus 1 at the end. This is the size of the array, which is approximately how big? This is 1 million entries. Do you think an array with 1 million entries is big?
No.
No. What is the population in Sacramento?
It's over 1 million.
Oh, it's way over 1 million. Yep.
Like 5
So
million.
like 5 million. Okay. So there you go. So 1 million is not really that big of an array. So my algorithm in this case will take 20 comparisons, taking 20 units of time. Peter's algorithm, predictably, will need exactly that much time. And Peter's saying, I'm still winning. Well, let's just make it one more, right? 2 to the power of 21 minus 1. I need exactly 21 times. Oops, I should have done it the lazy way. That's the lazy way. And Peter is just losing out by 10 units of time. So Peter says, that's not fair. Well, okay, if it's not fair, let's make the number bigger. 2 to the power of 22 minus 1. I need 22 comparisons. And Peter will need a lot more. He is losing faster and faster and faster. Okay? Hwhy do you think this is happening to Peter? What
Exponentially.
Well, it's not exponential. Surprisingly, his algorithm, or the amount of time that his algorithm requires, is growing linear to the size of the array.
Right, but ours.
But the size of the array is increasing exponentially. It is my algorithm using the log of 2 of the size of the array, and that's why I'm winning. Okay? But that's kind of strange. Don't you think it is strange that I have a much slower computer to begin with, and I still end up being faster in the end? Why do you think that is the case? I mean, how did that happen?
Checking.
It has to do with the shape of the curve. Okay, it's not the constant. If you plot a curve, a linear line is like this. It's a straight line. When you plot log of something, the curve looks like this. Okay, so that means if you multiply a constant to the log curve, all you're doing is stretching out the curve like this. It will only delay the inevitable. In other words, with a smaller constant, I will beat Peter faster. With a larger constant, I will beat Peter a little bit later on, possibly at about this point here. But I will beat him eventually. I just need to pick a larger array, and I will be able to beat him.
You could beat him from the first time if you had a computer.
Yes, but that wouldn't be very fun, right? I mean, I like to torture Peter, right? Got it. Okay, so this is an important topic. This is called the time complexity of an algorithm, which is loosely translated to how is the execution time, what is the execution time proportional to? In this case, my algorithm is proportional to the log of the number of elements in the array, and Peter's algorithm is proportional to the number of items in the array, and that's why he lost. I know we are going a little bit over time, but the important part of this piece is not theoretically speaking, what is the log of something. There's no theoretical importance. Okay? The practical importance is you need to know what the time complexity is for any algorithm that you choose, because if you choose the wrong algorithm, it will take a lot longer to execute, and someone who's choosing a faster algorithm will be able to beat you. So you will end up losing your job, and that's not theoretical. Okay, that's the bottom line. So next time we'll go back and take a look at this example again. We'll go to Wikipedia and see how we can find out the time complexity of known algorithms. So we don't have to invent the algorithms. We just have to know how to evaluate the algorithms. Okay, we'll call this Tech versus Peter.
I think Wednesday night.